Here we go. Good afternoon, good morning, and good evening, everybody. Welcome to today's Octio webinar. My name is Rajan, Vice President Sales and Commercial at Octio, and it's a pleasure to have you today for our today's webinar. The session today is focused on a deep dive of the 4D gravitude and subsidence monitoring technologies as a follow-up session of the introduction technology, which we did a few weeks ago. We'll focus on the applications to improve the subsidence monitoring and understanding of the subsurface and help us to reduce the field development costs. During this unprecedented COVID-19 period, most of our customers continue working from home and many industry events have been delayed. This webinar forms part of our digital strategy to continue engaging our customers and share the latest technology updates. A full schedule of our upcoming events is available on our website, octio.com. Just a few comments about today's session. So we aim to spend 25 minutes for presentation, followed by 15 minutes for Q&A. As today's session is mainly focused on the deep dive for the 4D gravity and subsidence monitoring technologies, we'll quickly summarize the technology and then focus more on the case studies and the value proposition for our customers. I would like to remind that the recording of the introduction webinar is available on our website. In addition to that, we'd love to have some feedback and questions from your side. So please don't worry about taking notes. We will be sharing the slides and after the session. And any questions, please type in the chat box. We'll aim to go through as many of them today. And if we cannot answer any of the questions, we'll come back to you in the upcoming days. So we look forward to have a very active webinar today. Your next slide, please. All right, so just to get the ball rolling, as many of you know, when we talk about Octio Gravitude, we are talking about the technology company with the industry-leading expertise in microseismic monitoring and gravimetry monitoring. We have two distinct business units at Octio Gravitude. On the right-hand side, we have the Octio business unit with two key offerings. The first one is WellWatch, which is passive microseismic monitoring to improve the injection and hence recovery rates. And the second one is our latest offering, DrillWatch, which is basically active microseismic monitoring using drill bit as a source. This technology eliminates the need of active seismic sources compared to conventional technologies and help us to identify the bit position as well as look ahead of the bit. On the second part of the business, we have on the left-hand side is the Gravitude side with two key offerings. First, we have the depth watch, which gives an idea about the seafloor deformation to understand the reservoir compaction and identify undrained reservoir compartments. And the second is our key flagship offering, G-Watch, and the focus of today's webinar. It has two parts, 4D gravity, which is sensitive to mass changes within the reservoir, and seafloor subsidence, sensitive to reservoir compaction. Combining these together, we get a time-lapse measurement for reservoir monitoring and management. And the key message I would like to pass is this technology gives the same value proposition as a 4D seismic, but at 1/10 of the cost. With the company introduction, it's time for me to introduce today's speakers. Jon, thank you. So we have today here Jon Yvonne Lingard, Vice President Sales and Business Development. So Jon is focused mainly on the business development at Octio Gravitude. He is geophysics with background and has done multiple different management roles within Octio Gravitude and has been one of the early members of the company. Also, I have Martha with me. Martha is Senior Geophysics with Octio Gravitude and has been one of the driving forces for developing and taking the Gravitude technologies to the next level. Jon, Martha, welcome to today's session. I'm excited to have you guys today.
Thank you, Rashan. All right. Maybe I should take it from here then.
Yes, please. It's all yours now.
Fantastic. Thank you. So as Rashan mentioned, we have about 25 minutes lined up for this presentation. We will, even though we had a bit of an introduction in the last webinar, I will give some introduction about the GWatch technology as a summary. I will talk a little bit about the typical strategy for conducting these surveys in the field. I think it's a good idea also to talk a bit about the sensitivity of this technology and also how it has developed during the last period in time. And finally, obviously, to get into more details on case studies. We showed some case studies at the last webinar. We have some more case studies that we want to talk about today. So, as already been mentioned on the last webinar, the GWatch technology is conducting of two independent monitoring tools. One is gravity, where we are monitoring mass changes in the reservoir. This allows us, as mentioned, to understand a little bit more about the dynamics in the reservoir itself. This can, for instance, be how fluids are redistributed during the period of production, and also how hydrocarbons have been depleted over the field, and as also mentioned, how the driving mechanism is evolving on the field. Are we seeing aquifer coming in and supporting, giving pressure support? Is it compacting, and so on and so on? The other part is, of course, seafloor subsidence, which also is sensitive to reservoir compaction. And it's also possible to understand a little bit more about how the pressure and pore compressibility is distributed over the reservoir. And of course, another very important factor of the seafloor subsidence is that when the seafloor is subsiding during a time-lapse period, so if we are monitoring at one given part in time, it's very important to correct the 4D gravity signal for kind of the change in depth from the seafloor subsidence. So it is also a very important parameter to monitor in order to get the correct 4D gravity signals. And with these two technologies monitoring, we are able to get kind of a lateral map where we are understanding these different evolutions in time over the reservoir, and we can understand, for instance, things like lateral compartments over the reservoir. And as Rashan also mentioned in the introduction, these techniques are quite cost effective, being costing only a fraction of the cost of traditional 4D seismic. So again, this is a technology that uses a ROV during the survey. So we have the technology is actually inside this sensor frame, where we have both the relative gravity meters and also pressure sensors. And when we are doing a survey, we are actually visiting different concrete platforms that are distributed over the fields. So we are visiting these concrete platforms maybe one or two times during a survey in order to get some good understanding of how the gravity signal and also how the seabed deformation has changed during a certain period of time. So I will get a bit back to how this is actually done in this slide. So survey strategy. So it's not random where these concrete platforms are located on the field, obviously. So This is from a map coming from a publication on the Ormen Lange. So here you can see the rim of the Ormen Lange field. You can also see how the different concrete platforms have been placed over the whole field. So we can observe that there's quite a bit of measurements taking place inside the reservoir rim, but there is also quite a bit of measurements that are being measured outside the reservoir rim. And these are actually what we call zero level stations. And this is actually quite important for us, because this allows us to understand the resolution of this technology. I will come back a little bit to that after on the next slide, but it's very important for doing in situ calibration. We are also deploying tide gauges at a subset of the stations to understand how the tides are evolving during the survey period, and this also allows us to compare the different vintages of the monitoring. And as already mentioned, we are visiting all these stations at least twice per survey. The distance between each of these stations is kind of a rule of thumb. It's about the same as the depth of the reservoir. So if the distance from the seabed down to the reservoir is 2 kilometers, then it makes sense to locate that the spacing between these two is around about 2 kilometers. If it's lower, you can place them even closer. That's in order to get kind of most out of the data at the end. So a couple of mentioning about the zero level stations. So as mentioned here, if we are thinking of all these, so if we do one baseline survey and we do one monitor survey, and we try to plot all the different zero level stations on a line as a function of depth, in an ideal case, we would expect to have a kind of a flat line. But of course, in the field, there are differences in for instance, density contrast in the water. For instance, things like the water depth, the tiny differences in water depth, and this actually causes some offset and some slopes, and this is something we are obviously observing, and this allows us some ways of calibrating the measurements between each of the different vintages. And when we do that, we can actually correct it back to a zero level. And that's something we are of course doing the calibration on the zero level stations, but this calibration is applied to all the sensor stations over the field itself. And at the end of the day, this allows us to get a better handle on the uncertainty of the data. Marta, do you want to give some additional comments here?
I could just maybe mention that the main objective of this survey is that we want to measure the time-lapse changes in subsidence and time-lapse changes in 4D gravity caused by production-related effects within the reservoir. And to achieve this, we need to correct for all other variations or effects that can introduce a 4D signal in gravity. And that is kind of the main role of these zero level functions. They provide a means to actually measure and correct for any changes if it is the average water level, as you mentioned, or if it's tiny offsets in the calibrations of the instrumentation. These zero level stations allows us to measure and correct for these effects, such that we are left with only the 4D gravity signal in corresponding to mass changes within the reservoir.
Thank you.
Yeah.
Thank you very much. And so when we are conducting the service in the method as described, typical application of gravity is as demonstrated in this very simple sketch here. So before, for instance, a gas field starts production, we are conducting a baseline survey. As time is passing and we are producing this orange area of gas, and with time this is actually allowing aquifer water to enter into the reservoir, and as water is entering into the reservoir, this is obviously causing a positive evolution of mass inside the reservoir, since water has a higher density than gas. And what is obviously happening when you are draining gas and entering more water, these gravity measurements that are done over these stations located here, the concrete platforms located here, we will observe a positive change in gravity, while in this area here we will see less positive, but still positive, because some of the areas below here is affected by the evolution of water into the reservoir, while this station here on the left will not be able to measure these type of changes, because they do not exist there due to this sealing fault. So from this very simplistic sketch, for the gravity will have the ability to measure the aquifer strength. It will be able to detect undrained compartments, and it will also have some means of calculating the hydrocarbon volumes in the field itself. The same way we can consider a very simplistic sketch for subsidence monitoring. Again, monitoring a field where hydrocarbons is being produced, either gas or oil, and with time these reservoirs will compact. This effect we are able to measure on the seabed, as demonstrated here, and this type of information about coming from subsidence will allow us some means of understanding things like compressibility, pressure drop, and also permeability inside the reservoir. It will give some means of understanding excuse me, when you have a window to perform, for instance, infill drilling, identify undrained compartments. So you can see that seeing these compartments can actually both be seen from for the gravity, but also subsidence. So this is a way where the method is it's two different methods to identify it, but one way is obviously to see changes in the subsidence signal over the field, but the other one, as mentioned on the previous slide, was to see changes in fluid and detect it that way. A third, or actually a fourth application of subsidence is obviously that when you are measuring something at the seabed and you're trying to explain things that are happening in the reservoir itself, you are also able to say something about what's happening in the overburden, and you can improve the geomechanical model. We will come back to that actually on one of the case studies afterwards. But in order to do this, you obviously need some information from, for instance, from wells. And of course, 4D seismic can also be helpful in this type of applications, as I will show later. There is, of course, quite a bit of field cases out there already. And without using too much time of this, you can see that there's quite a bit of different applications that are motivating the different monitoring projects. So these are mainly lists from the Norwegian continental shelf. But we have tried to highlight the main applications for doing these surveys on the different fields. And you can see that they're highlighted in different colors to highlight what part of the application is coming from subsidence and what part is coming from 4D gravity. I think it's also worthwhile mentioning that you see that there's a large variety in, for instance, burial depth. So burial depth is the distance from the seabed down to the reservoir itself. There's also big differences between sizes of the field, and this is obviously demonstrated with the number of concrete platforms distributed over the fields itself. And you can see that some of these fields, they are actually monitoring without using 4D seismic at all. For instance, Åslandsten is one of these examples that we started the monitoring in 2018. And I think it's because many of you have learned about gravity and how this data can be very helpful, for instance, in 3D mapping of the subsurface. But there's quite a bit of difference between the different technologies that are used for this purpose. So just a very simplistic figure again, showing the differences between airborne gravity and getting down to stationary gravity measurements, as is what we are working with here. And also evolution in time, where the technology started in 1998. This was developed internally in Statoil at the time being, and how it has evolved until this period in time, where we are actually have a sensitivity actually below 1 microgal. And 1 microgal is a number that kind of allows us to resolve, for instance, gas-water contacts with sub-meter resolution. And the fact that we have been able to improve this technology so much over the years, I think over the last 5 years we have improved the sensitivity with a factor of 5. But the value of that is obviously that when you are observing these differences in the field, and you have a higher sensitivity, this can allow you to resolve smaller changes in the reservoir. So this way, technology development is actually directly linked to bringing more value into the interpretation of these data. So one example on the sensitivity evolution from Snøhvit and Albatross. We have acquired 3 gravity surveys to date in 2007, 11, and 19. And looking at the average uncertainty between 2007 and 2011, you can observe that these numbers here are more or less following the same scale as we saw on the previous slide, with the average uncertainty of, for instance, on gravity on 3.7. Introducing improved technology and deploying that in the field in 2019 allowed the sensitivity, the time-lapse sensitivity, to go down to actually 1.6. But of course, when you are conducting a time-lapse survey, it's not only the 2019 data that is affecting, but also the 2011 data. But looking forward with the sensitivity the technology has now, we expect that the technology will be able to provide average uncertainties that are going, and improving quite significantly. And I think it's quite important in this slide just to mention that the reason why we're able to make these improvements in, for instance, the time-lapse sensitivity in gravity is highly related to the instrumentation we are using and also the way the surveys are being conducted in the field itself. So it's a constant improvement for each and every year, but that is the value of these improvements is obviously demonstrated, as we can see here. So I will go through a couple of case studies now. First of all, I think it's quite interesting to look at. It's a bit old publication from 2014, but it's still very interesting. And one of the important things to mention about Malonga is that, as you can see on this map here, the water depth on Malonga is actually varying quite a bit, from about 300 meters down to 1100 meters. And there's back in 2012 there was some big uncertainties connected to a water breakthrough and compartments on the field, and this had some impacts on the understanding of key decisions to take on the field related to, for instance, infill wells and compression facilities on the field. At that time, it was quite challenging to see that, for instance, 4D seismic could bring the value needed for taking these specific decisions, and it was also a challenge to do this with 4D EM, because it would take too much time before time-lapse signals would be resolvable with 4D EM. There was obviously also some quite interesting factors on Malonga coming when we did the monitoring of gravity and subsidence on the field. And one of these things that is worthwhile mentioning is this pycnocline. And the pycnocline is actually the border between more salty Atlantic water and more fresh water. And obviously this pycnocline is basically referring to a density contrast within two types of water. And what was observed in the field was actually that this pycnocline was varying up to 150 meters, going up and down. And this obviously had a big impact on both the gravity and subsidence data we were able to obtain. So it was actually a quite important factor to monitor the location of this pycnocline. But implementing this type of information to the processing actually allowed us to get very good uncertainties, both with regards to for the gravity and subsidence monitoring. So even though there were some challenges, we were able to obtain very good results on Malonga, trying to actually fulfilling the intentions from the planning. Going on further, this is from a publication in 2017 on Malonga. It was actually quite critical to understand reservoir compaction, and in this sense, the subsidence data obtained from the surveys we have conducted was quite crucial. Feedback was that at the given field with the given challenges with 4D seismic imaging, the time shifts from 4D seismic was not accurate enough. And here we can see how this is a map between 2012 and 2014 about subsidence, and we can see how the seabed is actually subsiding, and you can see that there's more subsidence close to the areas where you have producers, and this information you can use to say something about the compaction of the reservoir itself. With the 4D gravity, this actually gives a quite immediate insight to the mass balance itself on the field. And for instance, here you can see a map of the gravity change between 2012 and 2014. And again, these blue circles here are indicating areas where there's an increase in the gravity signal, and the circles in red is indicated with places where you have a decrease in gravity. And what you can immediately see from this type of map is that you have water entering in from the east side of the field, generating this evolution of positive mass change in the reservoir itself. And this information can quite efficiently be integrated into a history matching workflow on the field to make even better reservoir models and better prediction about the future expectations from production. At this field, it's quite interesting also to mention that 4D seismic and 4D gravity is used together and work as complementary information. The monitoring techniques is obviously quite different and also independent. When you are introducing such a workflow, you can actually, one of the things that has been done is to acquire less frequent 4D seismic and use gravity in between the seismic acquisitions. And this is another way of doing cost savings, since 4D gravity is less expensive than 4D seismic. Quite interesting case to mention is Stockwell, which is an oil-producing field. So subsidence at this field has kind of been the main motivation for running GWatch on the field itself. So in this field, subsidence is used for both understanding the aquifer properties and look for undrained compartments. And what is quite interesting here is coming from a publication by Thomas Røste and Kjær. I think it's from 2017. And this publication is showing how the subsidence monitoring on Stockwell is used for calibrating a geomechanical model. So both subsidence data and also measurements taken from platforms on the field. So by using these data of subsidence, it's possible to model the seismic 4D time shifts in the overburden based on the existing geomechanical model that has been obviously calibrated for subsidence. And then by comparing the modeled 4D time shifts with the actual 4D seismic observation, this type of information can be used to indicate, for instance, undrained areas in the reservoir itself. So that's kind of a different workflow where actually these data types are integrated together in order to make lateral predictions of the reservoir behavior. We have another case here coming from Snøhvit and Albatross. This is a field located in the central part of the Hammerfest Basin in the Barents Sea. Water depth around about 300 meters. The reservoir is containing both gas condensate and oil in the lower and mid Jurassic. And you can see that there are some minor changes between the Snøhvit and the Albatross field. It's with regards to depth and also geological deposition environment. The production on the field is run by depletion, and there's actually quite a few production wells at Snøhvit, actually 7, and only 3 on Albatross so far. So we have actually published this example at the SCG just short time ago, and I thought it was interesting to actually go through this example and say something about the data quality that was obtained in 2019. So we have a situation where each of the stations is visited multiple times during a survey, and this allows us some information about the precision of the data. I think this is a good place to introduce Marta, who has been a bit more involved in the processing, so she can give a more in-depth explanation of these slides.
Thank you, Jan Evan. So what these plots are showing you is actually the difference between, as Jan Evan mentioned, for each time we visit a measurement location, we measure we have 3 sensors. So we have 3 records in one measurement. And in addition, we come back to this same measurement location multiple times during the survey. And it's based on all of these repeat measurements that we compute a station mean, which is the 4D gravity or relative depth value for that specific, the relative gravity or the relative depth value at that station in that vintage. So what these plots shows you is for each of the individual measurements, the discrepancy to this station mean. So this gives you a handle on the repeatability in your measurements within one vintage. As you can see, there is no trends in time, and the top plot here shows the results for pressure in the data collected in 2019. That's the Snøhvit and Albatross, and it shows the range of 3 millimeter. The bottom plot then shows you the corresponding results for relative gravity, and you see that all the residuals are within 1 microgal throughout the survey. The x-axis here is decimal day, which is the number of days since the start of the year. So it's a function of time. So this is based on all this information, we can then compute the repeatability within each vintage, both in pressure and in gravity. And that feeds into the uncertainty quantification for the time-lapse results, which is the topic of the next slide. So what you see to the right here is actually the subsidence measurements for the individual measurement locations above Snøhvit and Albatross in the 2011 and 2019 vintage as a function of relative depth on the x-axis here. And the measurements at the 0 level stations are indicated in green here. So what is, and the arrow bars gives you the standard deviations in the data. As mentioned by Jon Even, the uncertainty in these results are dominated by the 2011 data vintage, but it is at the level of millimeters in subsidence and in our 1.6 microgal in gravity. And what we see when looking at these measurements at the zero level station is that they are statistically comparable with the null expectation that we have, and that actually the spread in these, so the spread in the values of the zero level station gives us an estimate on the time-lapse uncertainty in the data.
If I've understood correctly, Marta, is it also so that the thickness of these error bars is plus minus 1 standard deviation? Did I understand that correctly?
Yeah, it is.
Yeah.
Correct. Yeah. So so this so as we see for this particular vintage, the average subsidence results is at the order of 1 centimeter, and for gravity it's up to 10 microgal, the time-lapse signal within this time period. So which brings us to the next slide, which shows these results in a map view across the field with one value for each of the measurement locations. And this is the subsidence results in this plot here. And the scale of these bubbles are indicated with this gray point. So as you saw from the previous slide, they cluster around 1 microgal. So as Jon Even mentioned, measuring subsidence data is actually a seafloor observable of the reservoir compaction. And coupling that to pressure data from wells enables you to constrain the poor compressibility of a reservoir. And for Snøhvit, this the poor compressibility was one of the unknowns in the reservoir model, and utilizing this data enabled them to reduce the uncertainty in these parameters from in the range between 1 to 8 to 2 times 10 to the minus 5 over bars. So almost an order of magnitude reduced uncertainty in that parameter. And the explanation for the relatively low compressibility of these fields are then anticipated to be because originally it was actually buried 1 kilometer deeper than what it is currently.
Yeah, thank you, Marta. And I think also talking about gravity change, I think it's fair to say that this data has had a quite big impact on the model quality. Just from a qualitative point of view, there is some kind of straightforward examples of where we can, make some observations on the data itself. For instance, this area here where I'm pointing at, you can see a positive change in gravity. And this is actually a direct indication of communication over 2 small faults located in this area here. And since you have had water influx here, this is an indication that this segment has actually been produced and have observed water influx. This data is actually also providing quite a bit of value through history matching and actually allowing us some quantitative constraints on quite a bit of different parameters. I don't know, Marta, are you able to give some more insights on this history matching process?
I can maybe say a few words on the overall workflow. So the first step is typically to estimate this pore compressibility parameter with a higher accuracy, as indicated for the subsidence data, and then having a qualitative assessment of the data, as you mentioned, to identify what are the main uncertainties in your reservoir and what families of models can we actually exclude, and then doing after that a quantitative estimation on the value of some of the key uncertainties in the reservoir. And this quantitative part of the history matching workflow then for the gravity is typically combined with production data from wells, where you do a joint inversion, for instance, for pore volume multiplication factors, the relative permeability of your reservoir, or the aquifer communication or volumes. But it's, yeah. I hope that was, yeah.
Thank you very much. Thank you very much. And that actually brings us in for the landing now, and give a couple of conclusions and outlook. And I hope through these slides we have demonstrated a bit how this type of monitoring can actually map a bit when it comes to the movement of the fluid contacts and the depletion, understanding the driving mechanism of the field, understanding key parameters as, for instance, the pore compressibility of your reservoir, and also how this type of technology can be used for identifying, for instance, undrained compartments. As Marta mentioned on the last slide, it's also quite easy to incorporate this type of data into history matching workflows. And all in all, this allows both qualitative and quantitative both guidance and constraint into the workflow. But at the end of the day, it gives quite a bit of an improvement in the reservoir model, and again leading to optimized production. So with that, I'm very happy that you had the time for joining this webinar, and now we are very keen on looking into questions.
Yeah, Jon, Marta, thank you very much. It was a really good session, and thank you for sharing your insights. I would like to highlight we have really good participation today, not only from continental Europe and Scandinavia, but also from our friends across the border, and all the way from friends from Australia and Far East. So special thanks to you guys for staying late with the time change. I know it's quite late there. We didn't plan very well when we were planning the time. We forgot about the time change in Australia. So thank you. We have quite a few questions in Q&A and chat, so we are kind of running short on time. So we'll try to go through a few of them today. The first one is coming regarding mainly for the zero level stations, Marta. So how far from the edge of the field boundary must they be?
So this is a good question. Typically, this is determined through modeling, and its answer is field specific, where you model the anticipated extent of the subsidence bowl and also the reach of the 4D gravity signal from the reservoir, and then you position them outside that area. But of course, it's kind of a there is also a cost implication related to that, so you will have to make some adjustments. That's a fair I've lost the English word. Yeah, balance the cost and the data quality impact. But as we have seen from the field studies that we have done today, it's typically about 5 kilometers away from the rim of the field, but it will depend on the burial depth of the field and also the magnitude of the signals that are anticipated. But this is something that we will we can assess through forward modeling based on the specific field properties. Yeah.
Thank you, Martha. It's going to be a rapid fire round, so I'm going to go through quite fast. So next question. In your opinion, what makes 4D gravity better than 4D seismic in some of the fields?
One main advantage with 4D gravity in comparison with the 4D seismic, it's that it's unambiguous in the way that what we measure directly is the mass changes within the reservoir. So there is no competing signal from, for instance, the pressure evolution within the field. So that gives you a direct, so 4D gravity gives you a direct handle on the mass balance of your reservoir. So it's more quantitative, you could say. And also due to the relative simplicity in the forward modeling, you have a linear relation between the mass change and the corresponding 4D gravity signal at the seafloor. That makes this incorporation into the, or using it in the history matching workflow more straightforward and at a faster time scale relative to when you acquire the data. So yeah, I can go on, but maybe
we
in
have
some cases, of course, it's advantages to have both, but and in some cases, 4D gravity will answer the main questions you have with your reservoir. It depends a bit on what's the main uncertainties.
So we have a couple of questions put together in one. It's more related to operations. Are there any specific vessel requirements? What is a typical operational workflow for a survey?
We will typically the workflow is that we have an operational manager within Gravitude that is the project lead on our side, and the client typically arrange with a vessel, and then we facilitate all the interfacing through the vessel with the vessel and the acquisition part of the survey. Requirements on the vessel, it's more on the ROV. We currently need a working class ROV to position the instrumentation at the seafloor. Like staffing, for instance, during a survey, it's only 4 extra people from our side that needs to attend during the data collection. And the data collection depends on the number of measurement locations, but range between 1 week and 1 month, like in average. And then you get the results off the boat, and also the final processing results some months after the survey completion.
So that's really good, because I think you partially answered the next question. Was what is the turnaround period for the results? So you kind of partially mentioned that, and also it says what kind of support OctioGravitude provides for the data processing. I'm assuming we provide processing, but maybe it meant what kind of support we provide in integration. So maybe you can elaborate a bit. What can we do for the customers?
Yeah, so we provide off the boat results. That is just when the survey is finished with quite high quality, and then we do the full processing of the data to provide subsidence value and also 4D gravity signal value at each of the measurement locations across the field. After the first repeat survey, that is. And then we also can assist in the history matching workflow. Here we have competence in both the qualitative and also the more quantitative part of that work. That would be more on a consultancy basis, this integration part of the data.
Fantastic. I had another question in the chat. I see you already answered. What type of gravity sensors do we use? So we use relative gravimeters, CG6 sensors from Syntrax. I think we don't need to elaborate more on that, right? So it should be. Do you want to add anything more, Martha, on the gravity sensors?
No, maybe just
Okay.
mention that these are state of the art currently. So.
All right, so we're 11 minutes over from our scheduled time. We do have a little bit more questions, but I think we can reach back to our friends over email, and we'll share the slides, and we'll have the webinar recording available on our website, octio.com. Once again, thank you very much for joining us today. It's a pleasure to have everybody today. Have a nice day. Thank you.
Thank you.